Let's have a look at the CH 3.6 standard. So this is the first lesson for it. And I'm going to revise some background knowledge you should pick up from level 1 and level 2, which is ions and solubility rules. You don't have to know them, it just makes your life a lot easier though. Looking at what dissolving is, so you get this idea of tension between the cations and anions and water, and when they come out of solution and into solution, and then we do the calculations of solubility and the solubility product. So that's what we're hoping to get through today. So this is what you should know from level 2. If I give you a compound, sodium chloride is a nice easy one. You should be able to know that sodium chloride consists of sodium ions and chloride ions. So if you write the equation for it, you should be able to write sodium chloride solid goes to sodium aqueous sodium ions and chloride aqueous ions. Note for level 3, you should always write the statin, solid and aqueous. Okay. Knowing the solubility rules is actually also helpful, because when we mix two solutions together, if you sort of know what will be a spectator ion, because they're always soluble, you don't get sidetracked and you can focus on what's happening. So it is helpful, even though it's not necessary, it is helpful if you know it. Then last year you should have done the calculations of C is equal to N over V and N is equal to small m over big M. Both of you, these equations should have come across in the CH 3.4 standard as well, so it shouldn't be too unfamiliar. Then last year, if you did the chemical reactivity standard, the 2.6, you should have come across the equilibrium constant and Le Chatelier's principle. So just checking, have you done the 2.6 last year, even if you didn't sit the exam? That's the chemical reactivity one. Okay, so Caleb, you don't know pretty much anything about equilibrium constant, is that correct? Okay, right. Well, we'll sort of go over it and hopefully it'll make sense. So first of all, ions. I know it sounds ridiculous because by level 3 you should know all these ions off by heart, but unless you use them a lot, I can totally understand you forgetting them. So these are some of the ions you should know and recognize. If I say ammonium, you should be able to write NH4+. If I say phosphate, you should know it's PO4 3-. And as we go through this course, you should know that phosphate is actually the conjugate base of a weak acid hydrogen phosphate, which is the conjugate base of another weak acid dihydrogen phosphate, which would come under this column. I haven't put them all in. Don't worry if I lost you there. We will be, particularly next lesson, looking at that. Okay, so all of these ions, do they look familiar? Or are you going, I don't know? Okay, most. Great. So one way is to think of carbonate, hydrogen carbonate. You add a hydrogen. Hydrogen is normally a +1 charge, so you can see the charge drops from -2 to -1. So if you sort of group them, the same thing, sulfate, hydrogen sulfate, that's pretty good, phosphate, hydrogen phosphate. And as I say, you will in the next lesson see the dihydrogen phosphate, and then of course phosphoric acid, which is trihydrogen phosphate. Other ways to remember these things is ate a donut. Think of O and donut. So if something ends in 8, it has oxygen in it. And one way to remember how many oxygens and charge is in, say, sulfate, nitrate, chlorate, bromate, and all of those, is to think of School Chef Cook's Next Pancake, where the vowels are the charge. So if it's got 2 vowels, it's got a charge of -2, because this is only applying for anions, so it's minus. if it's the consonants are for the number of oxygens. So if it's got 3 consonants, it's got 3 oxygens in. So school, you'll see it's 2 vowels, 4 consonants, so it's SO4, 2 minus. So S for sulfate. CH for chlorine, so that's the chlorate. Pancake, phosphate. Okay, so 1, 2, 3, 4. So it's got 4 oxygens, and it's, yeah, thank you. There's an error there. That should have been 3 minus. Well done, Caleb. So that should have been PO4 3 minus, as you can see up there, and because there are 3 vowels. So it's good spotting. And then if you see an ite, oh, sorry, I thought I'd clicked. So an ite has got always fewer oxygens than an 8. So sulfate has got 4, ite will have less, so it's 3. And as you go down and you get even less, then we use the hypo. So for instance, chlorate, chlorite, hypochlorite, you can see the number of oxygens decreasing. Perchlorate means you're increasing. For the per is from hyper, so if you're like hyperactive, you bouncing off the walls, you've got so much energy, but we just use the per. So perchlorate means it's got even more oxygens. It can also mean that the oxidation state has increased. So if you've done redox chemistry and you've learnt about oxidation numbers, that is, where we can also use it. So for example, permanganate is MnO4 minus, which hopefully you'll know is that purple substance. Manganate is MnO4, so it's got the same number of oxygens, 2 minus, because it's got manganese has got a lower oxidation state. But you won't come across manganate at all in this exam standard because it's quite unstable. It changes to permanganate or manganese dioxide very quickly. Okay, so that's pretty much your ions, and there are a few more like chromate, dichromate, so I haven't put them all up here. But if you do want to learn more, remember the Quizlets. You can look up Quizlets and then just practice and play games, and just they're very good for rote learning. Okay, so are you happy with knowing your ions? Okay, good. So let's break them up. So if I've got silver chromate, okay, I know quite a few students will break this up as silver and Cr and O4, or they might say Ag, CrO and something else. So can you work out what the 2 ions are? It'll always be a cation and an anion, and normally the cation is a metal. It's only ammonium that's a non-metal cation. And then you've just got to remember the polyatomic ions. And silver chromate or silver dichromate comes up a lot on the exam, so that's why I put that one first. Correct, Caleb. Okay, except it's 2 minus, so it's CrO4 2 minus for the anion. Okay, but otherwise well done. Okay, so there you've got it, and I don't want to spend too much time, but if you were looking at the recording, you could pause the video and just do it. So you've got the potassium and chloride ions, you've got the sodium and hydrogen carbonate ions. So it's just, the trick is to know, you recognize that that's hydrogen carbonate, so you don't have Na and H and CO3. The calcium and sulfate ions, the ammonium and nitrate ions. So the ammonium is the only non-metal cation, otherwise the cations are always metals. Then copper and carbonate ions, and magnesium and hydroxide ions. You do need to get the formulae correct. So, if you said Cu plus and CO3 minus, it would be marked as incorrect for your equation and so on. So make sure you know the charges and that you can break it up, because you will have to write equations taking a solid and breaking it up into its ions for solution. So the next one was the solubility rules. Just as a general rule of thumb, the lower the charge on the substance, the more likely, all the substances are neutral, but if you think of an ionic substance, you've got cations and anions. So the lower the charge of the cation and anion, the more likely it's going to dissolve. Because can you imagine if I've got twice as much attraction in my lattice, it's going to be harder for the water molecules to drag me out. So aluminium salts, for instance, are insoluble because aluminium is a small ion and it has a positive charge of +3. So it's very hard to remove aluminium ions from a lattice, and so aluminium salts are pretty much insoluble. The smaller the anion or cation, also the more likely it's going to be insoluble, because again, being smaller, if you like, the charge is to cover less area, so it's more intense than if you've got a charge over a big area where it's less intense. So the bigger the anion or cation, the more likely it's going to dissolve. That, I must admit, is more for the polyatomic. So if I'm comparing carbonate and sulfate, for instance, or carbonate and nitrate. So carbonate and nitrate, it's CO3 2 minus and NO3 minus. Now, C and N would be a similar size, and they've each got 3 oxygens around it. So the ions are a similar size, but which one do you think will be more soluble? CO3 2 minus or NO3 minus? The NO3 minus, because it's only got a single charge. In fact, that's one of your solubility rules, is that all nitrate salts are soluble. Okay, the same thing with ammonium. Ammonium is a nitrogen surrounded by 4 hydrogens, which I agree hydrogens are very small, but they're adding bulk, and you've only got 1 charge spread over these 5 atoms, so it's much easier for the water to drag it out of the lattice. So ammonium salts, nitrate salts are all soluble, and group 1 are all soluble as well. So because they've only got a single charge. Group 17, which is the anion version, because these all form cations, these are anions. Group 17, yeah, pretty much those are soluble as well. Being smaller, particularly lithium, not every lithium salt is necessarily soluble. There are some that are sparingly soluble because it's a single charge over a very small ion. And so it's so although I've said group 1 and most lithium salts are soluble, some are not quite as soluble as, say, the sodium and the potassium salts. Okay, hydrogen, pretty much all the hydrogens ones are soluble, simply because it tends to form like an acid, like HCl and so on. Yep, so group 17, they tend to be soluble. Most of them are soluble, but there are exceptions, particularly when they bond with the heavy elements down here. So lead bromide is insoluble, silver bromide is insoluble, silver chloride is insoluble, and so on. Fluoride tends to be soluble. Okay, right, because it's I know it seems like a contradiction, but it tends to be more soluble. Right, and then, as I say, the oxides, the sulfides, the hydroxides, the carbonates tend to be insoluble because they got a bigger charge. They're all -2 instead of -1. These are -1, these would be -2. Hydroxides are -1, but it's still quite a small molecule. As I say, it's a general rule of thumb. It doesn't quite always work. Okay, so any questions on the solubility rules? And so, okay, you don't have to know them off by heart. It's just helpful if you've got that sort of idea in the back of your mind, that you know which ones. So these sort of, anything with lead, mercury and silver in it will tend to be insoluble. Anything with barium and strontium and calcium will tend to be insoluble. The smaller ones are not, actually. So there are a bit of contradictions. Right, so the next thing from level 2, is strontium used much? No. Barium is used a lot, and calcium, but I haven't actually seen strontium used very much in these sort of calculations. Strontium, of course, is used a lot in fireworks because it's a lovely red color. But that's beside the point. Right, so you have to know, of course, your calculations, and I know you both love these calculations, so that's great. If you forget the formula, as I say, think of the number of moles as a big muscle man, so double M holding up a small man. So it's the big M at the bottom and the small m at the top. So it's the amount in mole is the mass in grams over the molar mass, which is in grams per mole. And if I had grams over gram per mole, can you see the grams will cancel out? If I've got 1 over per mole, it's the same as mole. So please make sure you use your units to help you check whether you are supposed to multiply or divide. If you say get a blank in the exam, you do need to use units for excellence. It's good to use them throughout the calculation, but where they really look is at the end. Does your answer have the unit? Okay. Then think for concentration, think of a caret, okay, to get the N over V, and those are the units for concentration. The important thing is moles per liter. So sometimes they sort of trick you and they say they dissolve this much in 500 milliliters. Remember, you've got to then convert to liters. So just be aware of that. Volume is given in liters. And also what you will get at level 3, what you could get, is where you do the concentration, but not in moles per liter, but in grams per liter. So this is a mass concentration rather than the normal concentration. So they would have to spell it out. They would have to say, calculate the concentration of blah, blah, blah in grams per liter. So, they would have to specify if they wanted that. So you take the mass and you divide it by the volume in liters. So those are things you should have come across last year, perhaps not this equation, but this equation is just simply, you can see grams per liter, grams over a liter. Okay, so what I've got here are 2 videos now to give you an idea of what is happening when something dissolve. So here's my lattice of sodium chloride. So the greens are the big chloride ions, the sodiums are the small. And what it's trying to show there with the shaking is that there's this tension, this attraction between the positive and the negatives. When you add water, the negatives get surrounded by the water molecules. You can see the hydrogens are close by. And did you see there was a bit of tension? It's a bit like bowling balls. And can you see there's a tug of war going on? So this is what happens when it dissolves. It's the energy being released between the water molecules and the, if I just go, I could go start it again and I'll just move it on there and I'll, okay. So what I'm trying to show there is, sorry, it won't stay. Okay, is there's this tension and the energy is released when the attractions are formed between the hydrogens and the chloride, and that's releasing energy, and that's then giving enough energy to make it vibrate more so it can break that ionic bond. And of course, You notice it goes for the corners because there are fewer ionic bonds to break, so less energy is required. Okay, so have you got that sort of picture in your mind of something dissolving? Because when we talk about equilibrium, it's good to have that idea on the particle level. Okay, what I want to do here is now when a substance is in solution, so you can see I've got lots and lots and lots and lots of water molecules, and then I've got my separated ions. And notice the ions are hydrated. Can you see this chloride is surrounded by these ions over here? Sorry, these water molecules. Because notice how the hydrogen atoms of the water molecule are facing the chloride. So if I play this, you can see everything's moving around. And because everything's moving around, eventually a chloride is going to meet with a sodium ion. You'll see the grey of the sodium ion there. And did you notice an ionic bond formed there? If I go back a bit. Okay, so we're getting an ionic bond formed there, but there's this whole tension between the water molecules attracting it and this ionic bond. So in this example, it got pulled off again. But it can go back and then form a lattice, and then that can collide with another sodium or with another chloride and build up a lattice again. So we're trying to show this equilibrium, that there's this tension between the water and the ions, and so we have things going out of solution and into solution all the time. This is what we mean by equilibrium. Okay, so that's sort of showing it going backwards and forwards, and eventually, as I say, the sodiums and the chlorides will collide, and they can come out solution, and another one can go into solution. So that is looking at revising quickly level 2 stuff that you need to know. So are there any questions or anything you didn't know from what I went over? Okay, right. So this next thing is also sort of level 2, but we're looking at if I have my substance and it goes into solution, so my sodium chloride, it broke up, okay, and you saw that, then what would my concentration be of the ions? So if I have a salt sodium chloride, AB, okay, when it breaks up, I'm going to get equal amounts of A and B. So my solubility in moles per liter of chloride is going to be the same as my solubility of sodium. Do you agree? Yep. Okay. But if I have, say, something like silver chromate, as we had, because that was Ag2CrO4, then I'm going to get twice as much silver. So I'm going to have a concentration that's double that of my chromate. And then the other one is where it's the other way around. So this could be like magnesium hydroxide, where for every 1 magnesium, I've got twice the amount of hydroxide. So my concentration for hydroxide will be double. Okay, this is important when we have a pure substance dissolving in water. Then we can work out, if we know the concentration of my solution, I'll know the concentration of the ions. So if it's an AB salt, the concentration of the ions are the same. If it's a A2B salt, the concentrations differ where the A is double, and if it's a AB2, where it's the other way around. So example here is calcium sulfate, or silver sulfate, or calcium chloride. So please note that this is when I have nothing else present except pure water, and also I'm assuming that neither ion is going to react further with water. And don't worry, at level 3 you're not given those ions, so you won't be expected to do any calculations of those that react further. If you carry on with chemistry at uni, then yes, you will. But here you're only given ions that don't react further. Okay, so we've got these ions, they dissolve in water. So we can write an equation for that, and we can say there's an equilibrium between them. So if you think of those bowling balls that we had, okay, so the calcium sulfate is a lattice, water is added, and the water will try and extract some of the calcium and the sulfate ions. They'll be moving around and they'll collide with the lattice again and form a bond, and say perhaps another calcium will come off. So we've got this equilibrium. So some is dissolving and some is not. Now calcium sulfate is not soluble, okay, but we call it sparingly soluble because a tiny little bit will dissolve. So the water will be able to extract a few of the calciums and the sulfate ions. So that's why we can write this solubility equilibria, but it only applies for the sparingly soluble salts, the ones that aren't very soluble at all. Now, you haven't done with the level 2, but we can write a constant where we look at the relative ratio of the products, the calcium and the sulfate ions, to the reactants. So concentration of products multiplied together divided by the concentration of the reactants multiplied together. So it's just simply a ratio. So if I've got more of one, then the reaction can go backwards, and if I've got more of the other, then the reaction will go forwards. We get an idea of where that equilibrium position lies. Okay, and when as much as possible has dissolved, because remember I said it's sparingly soluble, then we say the solution is saturated. So just that you come across that term saturated solution, it means that you're not going to get anything more dissolving. We'll have a look at it just now. So if I have a big K value, looking at this ratio, do I need more products or more reactants? So just on a straight maths fraction sort of thing, I need, okay, if I want to have a big K value. So remember, it's products divided by reactants. So I want a bigger number on top, don't I? To get a big number over here. Yep, so it's products. So, you know, Kc2 over 1 is bigger than 1 over 2. So if I have more products, my K value gets bigger, so the more the equilibrium lies towards the products, then I've got a big K value, but the more the equilibrium lies to the reactants, then I'm going to have a smaller K value. Does that make sense? Yep, so it's just like a fraction, 2 over 1 or 1 over 2. So if I've got 2 of this and only 1 of that, then I'm going to have a smaller K value, because it'll be like 1 over 2. If I had it the other way, where it's 2 of this and only 1 of that, it's 2 over 1, so K is bigger. So I'm going to have more products for a bigger K value, and the equilibrium is going to lie more to the right. Okay, yes, it can be confusing. So I don't want to go too much into the equilibrium, but we only use the equilibrium for something we can measure, like as in concentration, because concentration can change. Can the concentration of a solid change? No. Okay, because once it's on a lattice, then it's on a lattice and it can't get closer or further apart. So we don't write in anything that has a solid in it, because that constant simply gets absorbed in, because it doesn't change, it just simply gets absorbed with this other constant. You write it in the equilibrium equation, April, but you don't write it in your equilibrium expression. So that's the equation, this is the expression. So if they ask you for an expression, they want something like this. If they ask you for an equation, you look at that. Okay. So, as I said here, the reactant is a solid, so that's constant, so we can absorb those two constants together and make another constant. And that constant we call Ks. S for solubility. So you'll come across later on Ka, that's a constant relating to acids, or Kb, that's a constant relating to base. It's all worked on the same principle, but we just give it a, an S or an A or a B so we know what it relates to. So if you get given a Ks value, you know that it's the solubility constant for an insoluble substance being broken up into its ions. So it's just because we've only got products, it's just the concentration of the products multiplied together. So Ks for calcium sulfate, you take the concentration of the calcium ions, concentration of the sulfate ions, and that's a given value. You can look up these values wherever, on the internet. You get all these tables of values. So you can see it's a pretty small number, 10 to the minus 6. So that's like 1 millionth, less than 1 millionth will dissolve. So it's a tiny amount, and that's why we call it sparingly soluble. Okay, so remember that's the expression, and this is the value. And then, of course, that is the equation. So if I say calculate the solubility product, I want you to calculate the value. If I say write the solubility product expression, I want you to write Ks is equal to, and then you write the ions down. Okay. So, and then the final thing is, for any equilibrium, it does depend on the temperature. If you change the temperature, you're going to change the position, because you're now adding energy into the system. So that, remember I said that whole thing about dissolving relates to energy. So if you're now adding more energy into the system, you're going to be changing how soluble something is. Okay. Now I see Caleb is typing. So this value has to be quoted, at 25 degrees. So when you get these lists of tables, it should say at what temperature it happens, because of course these things have been measured at all sorts of temperatures. The standard temperature is 25 degrees. Okay. Then also notice for the solubility product expression, we write the concentration by using square brackets. So you have actually come across square brackets now in a few places in chemistry. Square brackets can mean concentration, like over here. So you don't have to write concentration of, you just put the square brackets around the anion or cation or substance that's dissolved. Okay, and that immediately means concentration of. Where else did you use square brackets? You use them in the 3.4 in the Lewis structure of ions. So you use them there, and then seeing you weren't sure about level 2, you perhaps wouldn't have come across this one. The other place is in for complex ions, and we will be doing complex ions in the next lesson. So those are the 3 places that you'll use square brackets. Okay, right. So let's carry on with this. If I have an AB salt, so it goes to A plus or A2 plus, as long as it's a 1-to-1 ratio. So I've got 1 of A and 1 of B, so I can write the Ks for that. If I have the A2B, I'm going to have twice the A. Now remember when we said we've got to multiply it up. So if I've got 2A, can you see that's like A plus A plus B 2 minus? Do you agree? I could write out this thing as A plus A plus B 2 minus. So it's going to be, when I write this down here, it's going to be A squared, A times B, and so A times A is A squared. Okay, so when you write the expression, any coefficient that's in front becomes a superscript or a power of after the concentration. So if you had a 3 in front of the B2 minus, you'd put a 3, you'd raise the B2 minus to the power of 3. If you had a 2, you'd raise it to the power of 2. Yep. So just because you have to multiply all the products together. So it really is A plus A, so it's A times B, so it's A squared B. Okay. And then the other way is, of course, you've got now two lots of B, so it's A plus B, so it's going to be A times B, which is A times B raised to the power of 2. Okay. Now, please also notice, although I'm just saying this and I haven't been including the charges in my words, I have included the charges in my expression. Please make sure that you're very accurate with your charges. A lot of students get something marked wrong and they can't even get an achieve level because they've been sloppy with their writing. So if you are asked to write the expression, then please make sure you say like SO4 2 minus. Don't just say SO4 or don't just say AG. Okay, right, so very quickly, number 1, is it an AB, A2B or AB2? A2B actually, it's the other way around. Yep. Okay, because I've got 2 of this. What is this one, the aluminium phosphate? Yep, AB. So you got it now, April? So we've got 2 of the cation and 1 of the anion. Here I've got 1 of the cation and 1 of the anion. Okay, so it's just a straightforward AB. This is 1 cation and 1 anion as well. Okay, that's why I say you've got to know where to break it. This is also 1 cation and 1 anion. This is 2 cations to 1 anion. Here we've got 1 cation to 2 anions, and the same thing over there. So that's why, you know, I started off with, can you break up a substance? Because you'll be given a compound and you'll be asked to write the equilibrium equation, you'll be then asked to write the solubility product expression, and then you'll be asked to do the calculation. So you must be able to break the substance up into the ions. Okay, so here very quickly writing it up, and I'm just going to just put it in. Because I've got 2 of those, I have to raise it to the power of 2. Here it's a 1 to 1, so I don't raise it to anything. Again, it was a 1 to 1. Again, a 1 to 1. Here I've got 2 of them, so I raise it to the power of 2. Here I've got 2 chlorides, so I raise that to the power of 2. And here I've got 2 hydroxides, so I raise the hydroxides to the power of 2. So do you think you can write the expressions? Yep. Okay. So as I say, make sure that you're very accurate. Okay, yeah. Okay. So just make sure you're very accurate by also including the charges. Right. Now what I want to do here very quickly is look at this, and this is the FET thing. You can do this yourself. It's one of the activities where you look at how something dissolves, and you won't be able to see because it's so tiny. Can you see this? 5 times 10 to the power of actually no, I wanted I'm trying to look for the KS value, but it doesn't actually show it. Okay, but if I do this, no, actually this is not really what I wanted. Okay, I'm not going to do this one. I wanted to show you the ions if you've got the same KS value. But this is not going to help me. Okay. In your books, you'll see a true fit exercises for you to do, and they're quite useful to see what it looks like when you have something dissolved in ions in solution. So, yep. So, is it under designer salt? Okay, let me go here. Escape. Designer salt. Ah, there it is. Thank you. You've obviously done this. So, can you see if I have, I'm keeping my KS. Now, notice Americans use KSP. KSP and KS is exactly the same thing. You can see it's solubility product, SP. It's just different countries do use slightly different terms. But so don't worry about that. So if I keep my KS value the same and I shake it, it'll dissolve, and you can then see sort of how many ions are present. Okay, if I make, so this is a straight AB salt. If I now go and make it a B2 salt, and I'm keeping my solubility product the same, can you see how much more can actually dissolve? Look at it, it's still dissolving. So what I'm trying to say is you can't compare KS values if you've got different types of salts. You can compare a KS value of an AB with another AB salt, or you can compare a KS value of an AB2 or with another AB2, but you can't compare an AB2 with an A, because can you see, it's still dissolving. So this is a very soluble salt, even though the AB1 wasn't. So does that make sense? That it's going to be different and you can't compare. It's because, remember, you're multiplying those concentrations and you're squaring them, so it's going to affect things. So I just wanted to point that out. So I can see Caleb is typing, but okay. So, right. So, finally the calculations. With the calculations, there are two things you've got to watch out for. You've got to work out, do my ions come from a single source or do they come from two different sources? So if I have pure water and I add, say, lead chloride to it, where does the lead come from? So all my lead ions in solution, it comes from the lead chloride. Where does my chloride ions come from? Or where do my chloride ions come from? The same. So if they come from the same source, I can start using abbreviations and I can make assumptions. Okay, because I can just look at the ratio and say, lead chloride is actually PbCl2, so I will have twice the concentration as the lead ions. Okay, I can make that assumption because both of them are coming from the same thing, the lead chloride I added originally. But I can also get an insoluble salt by mixing two substances. So if I take lead nitrate and I pour it into a beaker and then I add sodium chloride, where does my lead now come from? The lead sulfate or the lead nitrate. Lead sulfate's actually insoluble, so it's the lead nitrate. And the chloride now doesn't come from that, it comes from the sodium chloride. Now, does that mean that the concentration of the chloride will be the same as the lead? Or double the amount, from the thing? No, because you're quite correct. It's going to be different because it's going to depend on the concentration of the sodium chloride for the chloride and the concentration of the lead nitrate for the lead. So then you can't make the assumptions. You can't say that the chloride is double that of the lead. So just read the question very carefully and work out, is it single source from the same thing, or are they from two different sources? So once you've got that in your mind, then you follow these simple steps. I call it the EEC method. Always write the equation down, because when you've got your balanced equation, you can see whether it's an AB, A2B, or an AB2 salt. In other words, where you've got to raise it. And then you can write the expression so that you can substitute into that expression. And when you've got the correct equation, you can have the correct expression, then you'll be able to calculate with hopefully no errors. Okay, so that was just, I'm writing, if you do this and you check your units and everything, you'll be correct. Okay. And I said I've made it equation first because a Q comes before X, okay, and E comes before K. So it's always equation, expression, calculation. Now, solubility product, as far as you are concerned, I like that, hopefully no errors, yes, I put that in as well. As far as you're concerned, the solubility product has no units. When you carry on with chemistry at uni, you'll find they tell you a different thing. But level 3, we're keeping it simple because they get quite complicated, the units. So we keep it very simple and we just simply say no units. So if you're asked to calculate the solubility product, please do not give a unit. Okay, this only affects excellence, by the way, because excellence looks at whether you've put units in or not. So if you put in a unit where it shouldn't have, you won't get excellence. Okay. You'll be given at least one concentration so that you can do the calculation. If you're asked to do the solubility, then you got to have your concentration in moles per liter. So you have to have a unit, and they have to give you a KS. Now it may mean that they give you in the exam like part A and part B and part C. So you may have to look at the intro, if you're busy with part C now, you may have to go back to the intro of the question and find the KS value there, because I've noticed some exam papers, they do just at the beginning and not during the exam, not during the question. So you may have to look for it, but it will be given if you asked for a solubility. Okay. And then, and this will be more in the next lesson, is calculate the solubility of a substance in the presence of a common ion. So if I've, say, got, let's say, a lead chloride solution, and then I add HCl, so I've got chloride and I'm adding another chloride, the solubility is going to change, okay, because I don't have the chlorides don't just come from one source anymore. It's changed. It's now gone to two sources. And then the other calculation is you have to predict whether you're going to get a precipitate. So if I mix this concentration of silver nitrate with that concentration of sodium chloride, will a precipitate be formed? So those are the 4 different types of calculations you can be asked. So, and they can be from a single source, and this is of course number 3 and number 4 are definitely from 2 different sources, because I'm mixing 2 different things. Okay, so let's have a look. First example. This is an AB2 salt, and I am given the concentration of how much will dissolve. So that's the solubility. I'm told to calculate the solubility product. So remember the EEC method? So you write the equation first. That'll make sure that you put the 2 in front of F, which hopefully will make you remember to raise the power of the fluoride concentration to F, to square it. Okay. Then you write the expression, because that means you're going to remember to square it. Okay. Any questions so far? You just take the calcium fluoride, divide it into its ions. If I've got 2 fluorides, the 2 goes in front, and then when I write the expression, the 2 goes as a superscript. Okay, now I do the calculation where I substitute in. What do I substitute in? Okay, first of all, this is what I have to calculate. It's always a good tip to try and remember what's your final answer going to be. Your final answer is you're trying to find the value of this, okay, the Ks. So what am I given? I'm given 2.3 times 10 to the minus 4. Now that is the solubility of calcium fluoride. So I can make some assumptions now, because every calcium fluoride forms one calcium ion. So what will my solubility of calcium be? 2.3 blah blah blah, correct, because one calcium fluoride forms two, sorry, I'm getting ahead of myself. One calcium fluoride forms one calcium. So the solubility, what I substitute into the calcium square brackets, is the 2.3 times 31 times 10 to the minus 4. What do I substitute into the fluoride? Not half, actually, double, because I've got twice as much fluoride. So for every one calcium, I've got one calcium fluoride, I've got one calcium, but I've got two fluorides. So if I've got two calciums, I'm going to have four fluorides. If I have 2.31, I'm going to have 4.62. Okay, so I have to double it when I substitute, and then I have to square it. So you do two things for fluoride. You double and square. Okay, so calcium is that, fluoride is that amount 2 times, okay, which is that, and then when you put it in, you have to square it. It gets bigger and bigger. Right. So in your books, I've given you the quick form. If you just have it from a single source and you have an AB2 salt or A2B salt, doesn't matter which one, then it's the same as saying Ks is equal to, make this S for solubility. This will be 2S, and I square it. So what is 2S squared? 2S times 2S is 4S. So 4S squared. 4S squared. So 2S times 2S is 4S squared. So 4S squared times S is 4S cubed. So a quick method, if you don't want to do all this long way, is if you recognize that this is a single source problem, you go, right, it's an AB2 salt, so you just simply say Ks is equal to 4S cubed, and you just substitute and off you go. So you just say 4 times this, cube the whole thing, and off you go. Okay. Right, so there I've, can you see there I've squared it? So that's that figure over there. Remember, when you're squaring a minus 4, then it goes, you know, you to the negative, so it's getting smaller, minus 7. And so you get actually a very small amount there. April, do you have to give reasoning? You do have to give some, for excellence, you do need to give some sort of, you can't just put the answer down. So, but you could just simply from here, you know, if you had that, you could just simply say Ks is equal to 4S cubed, and let S be 2.31 times 10 to the minus 4, and work it out and come up with the answer. And notice there are no units. Okay, because I'm doing a solubility product. Okay, right, so here is what the shortcut is. So if it's an AB2, it's S times 2S squared. So there it is. So you wouldn't have to do all that sort of thing. You could just recognize it's a single source, recognize that it's an AB2 salt, so you can go straight to Ks is equal to 4S cubed. And then it's the same thing for the A2B, you get to exactly the same thing. So both of these would be 4S cubed. If you have an AB salt, then it's going to just be S squared. So if I gave you silver chloride, it's AgCl. So if you had to calculate the solubility product, you would just simply take the solubility and square it, and that's your solubility product. Okay, so here is that same problem but with a shortcut. So remember, do the expression, do the equation, do the expression, because that will help you recognize that it's an AB2 salt. Okay, now you just put that in, and just be careful, you cube the solubility, you don't multiply by 4 and then cube. Okay, and then you get the same answer. So when you put things in your calculator, just double check, because some calculators do things in a very linear fashion. So if you have the 4 there, it might cube that too. Just make sure you know how to use your calculator. Okay, so here's now a AB salt, single source. So when you look at a question, ask yourself, what sort of salt is it? And it's single source. If it's single source, I can use that quick shortcut. Okay, so remember, break it up into the 2 different ions, write the expression, then you substitute. So here's the sort of long way, because you were given the solubility and I don't have a unit, or I can just say let S be equal to the solubility. S for solubility, that's all. You could have made it X or A or B or whatever you want to do it. And then you just simply use the shortcut, Ks is equal to S squared, square the value and get the same answer. Okay, and I recommend use a shortcut, but it's up to you. Okay, here now is also what? Single source or 2 different sources? Single source. So single source, you can use a shortcut. So remember, equation, expression. It's really important that you know what sort of salt you're dealing with. And then you've got that given. So for 1 iron hydroxide, you've got 1 iron but 2 hydroxides. So you've got to multiply that by 2, and then you've got to square it, remember. So that's a long way. Or you could go 4s cubed, cube the given value, the solubility, multiply by 4, and you get the same answer. So those, and you're guaranteed to get one simple thing like this, one single source question. I've never seen an exam paper without it, because that's what they give for the achieve level. You know, you've got to get this right at achieve, to achieve. Okay, now here it's the other way around. And I see we're on 4. I'll just go through this quickly so you can see the contrast. I've given you the solubility product. Notice there's no unit, and also notice it's a very small number as well. Calculate the solubility. So we're now going the opposite way. But you do the same thing, equation, expression. Okay? Now you say, my silver is 2s. Okay, I'm trying to find the solubility, so I'm solving for S. So there's my expression, and I just put in now, so I get to the 4s cubed, and that is equal to the given solubility product. So now we just work it out. I really recommend you divide by 4 first before you take the cube root, because if you try and do it in one step, students tend to make silly errors. So if you've got 4 on this side, divide both sides by 4, get that answer, then take the cube root. Okay, so now you take the cube root, and then you get that answer, and that is moles per liter. And you can, I mean, this is the shorthand form as well, because you're using the 4s cubed. Yep, so a lot of, sometimes I know when I mark, I sort of pull my head, but I know how easy it is when I can see a student's understood it and then they've done something silly, but we do it as well. Yep, April, always give to 3 significant figures. The only ones where it's not that important, this is assuming you're multiplying or dividing. Remember when you're adding, so like when you trying to calculate molar masses, you're just adding, or then you don't. Then you just go by decimal place. But the only other one where it's not that important is pH, because there is a way of getting significant figures in the pH, and unfortunately sort of people think it's too difficult for students to work out, and so it's a bit of a muck. So you'll find that pH values give to 2 decimal places, and then you'll make the examiner happy. Because the number in front is actually just the placeholder. So you know I get 10 to the minus 4? You know, if you took a log of that, that would then be 4 point something, wouldn't it? Well, if it was a negative log anyway. So the number in front for a pH is actually just the placeholder, and the numbers after it is what comes up over here, the 1.32. But if you give it to 3 decimal places, then the examiners don't like it.